Hi, I'm Hilary Watt from Imperial College. Confidence intervals, what are they? Why do we use them in medical research? We use them because we can't recruit everybody into treatment trials. Picture the scene. Doctor, can you recommend any treatment for my disease? Well, were you included in any treatment trials? Oh no. I'm an expert in patients who are recruited into treatment trials. I know nothing about how to treat anybody else. Puzzling. Why hasn't this doctor learnt about confidence intervals? Now imagine another patient, sick and in a hospital bed. He doesn't know anything about statistics, but he's also concerned. His doctor prescribed him a new treatment. The drug was tested on one patient that got the treatment and one that got no treatment at all, both with the same disease. This would be okay if by some crazy fluke the two patients in the trial and the patient in the hospital bed now were all identical triplets. Because people vary, we recruit several people to receive the new drug treatment. The results still vary to some extent based on exactly who we recruit. Confidence intervals are a way of quantifying the uncertainty based on random chance in who we recruit. Now here are some examples that lay the foundation for an understanding of confidence intervals. This graph shows blood pressure measurements in 20 participants who were selected at random from the population. Blood pressure was measured on each of them. The vertical axis is frequencies, so each bar represents 1, 2, 3 or 4 different patients. The first bar on the left represents one patient with a blood pressure of around about 110. The next bar is two patients with blood pressure of about 112 each. Forgive me for pretending we measure blood pressure this precisely. Because we know blood pressure on each of these 20, we can calculate their sample mean blood pressure, which is 128. But what we don't know is the population mean blood pressure, because we didn't measure the blood pressure on everybody in the population. It would just be crazily expensive. We've clearly got some uncertainty, therefore, in what the population mean blood pressure is going to be. There's a fair bit of uncertainty because we've got a sample size fairly small of 20, and the amount of uncertainty is reflected in this interval. So all values of blood pressure within the interval shown are compatible with this participant's data. All values for population mean within that interval are compatible. This shows a very much larger sample size of 200 participants, again selected by probability random sampling from the population. The calculated participants mean is 109.1, and therefore we might as well guess that the population mean is going to be around about 109.1, and because it's a big sample size we've got a fair bit of precision in this estimate, and so there's only going to be a fairly narrow range of values with population mean blood pressure, as shown here, which are compatible with the participants' data. Indeed, the values for population mean blood pressure that are compatible with the data are called a confidence interval. By convention we use 95% confidence intervals, which means that we've got 95% coverage of population mean values that are compatible with our data. We could have a slightly wider interval if we wanted for 99% compatibility or 99.9% compatibility, but by convention we nearly always stick with the 95% confidence intervals. I like to interpret with the following phrase: mean blood pressure is 109 in study participants. When we generalise beyond these to the population from which they were selected by probability random sampling, we're 95% confident the population mean lies between 107.4 and 110.8. If you know anything about the morality of medical research, you will know that participants are very rarely selected at random from any population, yet confidence intervals remain useful. We use them to account for random imprecision in random choices in who we recruit into our data. One way of putting that is this phrase here: 95% confidence intervals account for imprecision based on probability random sampling when we use study participants' data to estimate population mean, based on the assumption that participants are selected at random from this population. I'm still talking about the population, even though there isn't really such a thing as a population from which they were selected at random. But we do need to make that assumption of random sampling in order to be able to calculate confidence intervals. So we make that assumption because confidence intervals are so incredibly useful. accounting for random chance. However, if you want an interpretation that doesn't refer to the in-population, then I provide one here. Accounting for imprecision based on probability random sampling, we're 95% confident that the resulting mean lies between 107.4 and 110.8. The formal definition of a confidence interval is something really quite different, and it goes like this. When we select many random samples from the population and construct 95% confidence intervals around each sample mean, then, on average, 95% of these are going to contain the population mean. There's an illustration of 100 confidence intervals, each one shown by a vertical black line, with a cross showing the participant's mean value. The population mean value of 5 is shown by a horizontal blue line, and there's just 6 confidence intervals that don't include the population mean, which are shown in red. Therefore, 94% of the confidence intervals do contain the population mean. And that's very much in line with the long-term average of 95% of confidence intervals containing the population mean. This is a useful property of confidence intervals that everybody should know. And if you're doing an exam on statistics, you might need to quote a definition like this in order to get through your exam. Confidence intervals, talking about them, means that we're in the frequentist approach to statistics. There's an alternative Bayesian approach that I'm talking about now. As a frequentist, I've often taught people to interpret confidence intervals using the word 95% confident. I think, okay, that's good. But if you say 95% probable, oh no, that's really wrong. I've often said that. Maybe that's just word games, because confident and probable kind of informally mean round about the same thing. Some people get around that by thinking neither is okay and insist on the formal definition of confidence intervals, based on selecting very many random samples. Strictly speaking, what we've got is information about compatibility of population mean values with our participants' data. If you want to find an interval where we can truly say we've got 95% probability that the population mean will lie within this interval, then we need to combine 2 sources of information. We need prior knowledge about the probabilities for the different population mean values, and we also need information on the compatibility of the population mean values with the study data. These are named credible intervals, and this is the Bayesian approach to statistics. Now here's an example as to why it matters. Supposing we're estimating the mean blood pressure of everybody in the population of Bradford, but we've only got a tiny sample size, and the mean blood pressure is implausibly high in this really small sample for an estimate of the population mean for the whole of Bradford. So interpreting the confidence interval as 95% probable would be obviously wrong for people with practical knowledge about how blood pressure varies between different towns in England, and people that know that Bradford doesn't have sky-high rates of cardiovascular disease. They would realise that was wrong. But on the other hand, Bayesians often calculate 95% credible intervals assuming no prior knowledge, which technically is called non-informative priors. And usually these intervals are numerically pretty similar to 95% confidence intervals. So if you're informally thinking with your 95% confidence intervals that you've got 95% probability the population mean lies within the confidence interval, then you're along the right tracks. It's not quite technically correct, and it might not get you marks in an exam, but at least you've got a sense of what a confidence interval is. This is returning to my favourite slide about confidence intervals. It shows the spread of blood pressure between patients, which is quite wide, and then it shows a very much narrower interval, which is the confidence interval on mean blood pressure. This is because we've got quite a precise estimate of population mean blood pressure, so it's a fairly narrow interval with our sample size of 200 selected at random. The interpretation of a confidence interval, I like to start with a clear statement of what is true in study participants. So their mean blood pressure is 109 by calculation. And I do feel it helps people to understand confidence intervals by giving such a clear starting point. Then I talk about generalising beyond these to the participants from which they're selected by probability random sampling. This population is a bit of an abstract concept, and therefore I think it's worth repeating this interpretation over and over. And so when I teach statistics, I like to include this interpretation over and again in the teaching material. And if you're learning confidence intervals yourself, you might want to write down an interpretation such as this and put it beside your computer. This is different to the standard definition of confidence intervals, which you need to know, but I do feel this is of value because this is talking to the practical situations where we've got one set of study participants and we're wanting to make inferences based on that.